Now, you are entering our group presentation. Please welcome.
Adios. My name is Faiz Izzuddin, and my metric number is 215552.
Hi, my name is Waisul Lahrul. My matrix number is 217157.
We are going to present the graphite structure.
What is graphite structure? Graphite structure is a crystalline form of the element carbon. It consists of stacked layers of graphene, and the carbon atom in each layer are bonded through covalent bonds, with each carbon atom being sp2 hybridized. What is unit cell? Unit cell is the smallest repeating unit which shows the full symmetry of crystal structure. Unit cell of graphite. The lattice type of the graphite structure is hexagonal. The graphite structure consists of many flat layers of hexagons, with each carbon atom in the layer joined by strong covalent bonds to only 3 other carbon atoms. The layers are called graphene sheets, and the order of stacking is A in the hexagonal lattice. As we all know, for hexagonal structure, the length is equal to the width, but not equal to the height. Therefore, the angle of alpha is equal to the beta, which is 90 degrees, and for the height of the gamma, it is 120 degrees.
Next, the unit formula Z of graphite. The unit formula represents the simplest whole number ratio of the elements within the unit cell of a crystal structure. It describes the composition of the smallest repeating unit of the cell lattice, considering the arrangement and sharing of atoms within the unit cell. For graphite, which is composed solely of carbon atoms, the unit formula is simply a representation of the number of carbon atoms in the unit cell. There are 8 corners in a hexagonal unit cell. Contribution per corner atoms is equal to 1/8. Total contribution from corner atoms is equal to 8 times 1/8, that is equal to 1. Also, there are 6 faces in a hexagonal unit cell. Contribution per face center atom is equal to 1/2. Total contribution from face-centered atom is equal to 6 times 1/2, that is equal to 3. Thus, 3 plus 1 is equal to 4. The Z value for graphite is 4. This means that there are 4 familiar units within the hexagonal unit cell of graphite.
Next is the location of each atom in graphite. There are 2 types of graphite structure here, which is hexagonal structure and rhombic structure. This is the hexagonal structure of graphite. The ABS stacking order refers to the arrangement of carbon atoms in a 3-dimensional lattice, where the first layer is stacked on the top of the second layer, and the third layer is stacked on the top of the first layer. The ABS stacking order is considered more thermodynamically stable than the ABC stacking order, which is a metastable phase that can be achieved through specific conditions. For the rhombohedral structure, the ABC stacking order in graphite structure refers to the arrangement of carbon atoms in a 3-dimensional lattice, where the first layer is stacked on the top of the second layer, and the third layer is stacked on the top of the second layer also. The ABC stacking order has significant implication for various applications of graphene, such as high-frequency devices, flexible electronic and sensors, as it can be turned to achieve specific electronic properties.
Moreover, I will explain about coordination number of graphite. In crystallography, the coordination number of an atom is the number of the nearest neighbors it has. For graphite, which is composed of layers of carbon atoms arranged in hexagonal lattice, the coordination number is determined by the bonding within a single layer and between layers. In the graphite structure, each carbon atom is bonded to 3 other carbon atoms within the same layer, forming a hexagonal lattice, giving an intralayer coordination number of 3. For coordination number between layers, the layers of graphite are held together by weak van der Waals forces, and the arrangement of the layers follow an ABS taking sequence. Each carbon atom in one layer is directly above or below the center of hexagon in the adjacent layer. Each carbon atom interacts weakly with atoms in the adjacent layers. Specifically, in the idealized structure, each carbon atom is near 3 atoms in the adjacent layers. But these interactions are not strong covalent bonds. Therefore, due to weak van der Waals forces, these interactions are not considered primary chemical bonds. Thus, the coordination number between layers is equal to 1. When considering both intra and intralayers interactions, the total coordination of a carbon atom in graphite is equal to 4, which is 3 from within the layers and 1 from between layers. However, it's important to note that in many contexts, the coordination number refers primarily to the strong covalent bonds within the layer. Thus, the primary coordination number of a carbon atom in a graphite structure is typically considered to be 3.
This is the application of graphite structure. Firstly is the lubricant, second out and writing, and third is nuclear reactor. A lubricant is a substance that helps to reduce friction between surfaces in mutual contact. While the carbon atoms are strongly bonded together, the forces between each layer are weak. This allows them to easily slide over each other with minimal resistance. How exactly graphite be in art and writing? Graphite is a crystalline form of carbon and is useful as a writing and drawing tool, as only a slightest pressure is needed to leave a mark. Graphite being a moderator of nuclear reactor? Yes, graphite is used as a moderator in nuclear reactor to slow down the neutrons that are released during the fission process. This helps to control the nuclear reaction and prevent a runaway reaction.
An RBMK, or high power channel reactor, is a water-cooled nuclear reactor that uses radioactive uranium as fuel and graphite as a moderator to slow the speed of flying neutrons. But wait, doesn't graphite increase reactivity? Yes, graphite does enhance reactivity because it doesn't remove the neutrons from the reaction, it just slows them down. This type of reactor has 6 major parts: the fuel rods, the control rods, the graphite moderator, the pressure tubes, the steam generators, and the concrete shielding. The uranium fuel generates heat via nuclear fission, and then pressurized water is pumped into the core via tubes. The water then absorbs heat, which turns water into steam. The steam turns the turbines and generates electricity.